All right, this is section 4.1a, where we're going to be talking about antiderivative formulas. So let's review from what we know about derivatives. If our function is x squared, then what is f prime of x going to be? All right, we know that x squared is a easy function to find the derivative for. We simply use power rule. So power rule is, if we have u to the n, then our power rule is n times u to the n minus 1. And because of that, we know f prime of x will simply be, we bring down the 2 in front, subtract 1 from the exponent, so we get 2x to the first power. Now to put the steps that we did for derivative into words, first we bring the exponent in front to multiply, so we're essentially bringing the exponent down to multiply with our variable. Next step, the other operation we do is subtraction. Right? We subtract 1 from the exponent to bring it down from the second power to the first power in this case. Okay. So now we found the derivative. This semester is all about antiderivative, which essentially is undoing what we did with derivatives. So if we know that f prime is equal to 2x, if we know that the derivative function is 2x, then what steps can we do or can we take to find the original function? Right? So if we multiply and subtract to get to our derivative function, then we can simply undo these previous derivative steps to go back to where we came from. So instead of multiply and subtract, if we want to go back to where we came from, we're going to add and then divide. So we're going to add 1 to the exponent, and next we're going to divide by the new exponent. So we're essentially just undoing what we did with derivatives. So here is the power rule for integration. Okay. So you're going to see this integral sign, u to the n times du. Du is simply the variable of integration. This identifies the independent variable. So in this case, the variable we're using is u. Okay. So we're going to add 1 to the exponent rather than subtract. So u to the n plus 1 divided by n plus 1. Okay. And then this division is represented by this divided by n plus 1 plus c. And c is the constant of integration, which I'm going to explain a little bit below here. Okay. So let's consider something that we've seen before. What do you notice is similar between all these functions when we find all these three functions when we find the derivative? Okay. When we find the derivative, x squared plus 5 becomes 2x. X squared minus 13 also becomes 2x. And x squared plus 126 also becomes 2x. So we see that there's a family of functions which all share the same derivative. Okay. And so it doesn't matter what constant we have, as long as we have the x squared in place, then our derivative will all be the same, will all be 2x. Okay. So here is what I want you all to be able to see. Since we can add a constant to any of these functions and still result in the same derivative, the antiderivative of a function will just be in the form of f of x plus c to show that the family of functions that share the same derivative. So the integral of 2x will simply be x squared plus c, because there's an infinite number of functions that all share the same derivative. Okay, now the process that we just took is called antidifferentiation, or taking the indefinite integral. And this is something that we're going to be able to see later on. The indefinite integral results in a function, but the definite integral will result in a number. Okay, let's go to the second page. So here are the formulas that students will be responsible for. We talked about the power rule, which we're going to see with the examples below. There's also a rule with constants. So if I have integral of a constant times dx, then it will simply be the constant times x plus c. Right? Imagine you had 2x, right? 2x, the derivative of 2x is simply 2, so the integral of 2 will simply be 2x. So with derivatives, we're taking away, we're decreasing the degree of the exponent by 1, but with integral, we're adding 1 to the degree of the exponent. So initially, we have a 0 degree, and we increase it to 1. Okay. If you think about the derivative rule for natural log of u, will simply be 1 over u, right? So therefore, the opposite must be true. The integral of 1 over u du will simply be ln of u plus c. So anytime we have indefinite integrals, we also have to account for the fact that there's a family of functions that all share the same derivative, so we need to include a plus c. Okay. This is very important. The derivative and integral are simply inverse operations. So they have a way of undoing each other. So if I have a derivative function, and if I take the integral of a derivative function, then really these two operations are going to cancel each other out, and I'm just going to be left with the original function. Okay. Same thing, if I have an original function, and if I find the integral of the original function, and then I find the derivative of the integral of the original function, these two operations will cancel each other out, leaving me with my original f of x. Okay, so let's start going through each of these examples. Okay, so example 1, integral of 7x dx. Now the 7 is just a coefficient that we can pull in front. Really, we're just involving the x with the integral rule, with the power rule. Right? So the power rule says we start with a variable, we look at the exponent, we add 1 to the exponent, so initially it's 1. We add 1 to it, so 1 plus 1 is 2, and then we also divide by that new exponent that we just found, divided by 2. So our indefinite integral for number 1 is simply 7x squared over 2 plus c. All right, number 2, again, we're going to use power rule, but I'm going to go ahead and isolate the portion that we're going to find the power rule for. I'm going to pull the 7 in front, and we're just going to deal with this x cubed. So the integral of x cubed, we're going to use the power rule that you saw with rule number 1. X cubed, the 3 is my n value. So add 1 to the n value, so 3 plus 1 is 4, and divide it by that new exponent we just found. So x to the 4th over 4 plus c. Combine this to be 7x to the 4th over 4 plus c. All right, number 3. Anytime you have a plus or minus sign separating terms, we can treat each term like a separate function, and we can apply the appropriate rule for each term. So 2x, we apply power rule, same with 3x squared, and same with 5x to the 4th. So 2x becomes 2x squared over 2. With x squared, we get x cubed over 3, but we have that leading coefficient 3. With x to the 4th becomes x to the 5th over 5, but we keep that leading coefficient 5. And then finally, we're dealing with indefinite integral, so we have to include plus c. Okay, simplify down to x squared plus x cubed minus x to the 5th plus c. All right, number 4, we have to make some adjustments because we don't have terms separated by plus or minus. We have the parentheses with the exponent on the outside, so we need to first expand our binomial squared, and once we expand, then we can treat each individual term as a separate problem, but we first need to be able to get these variables out of the parentheses. So 3x minus 1 squared, the same thing as 3x minus 1 times 3x minus 1. I can expand this and FOIL. I'm left with 9x squared minus 6x plus 1 dx. So now I have individual terms, and now this looks a lot like what we did with number 3. We now apply the power rule for each term. So keep the 9, x cubed over 3 is the power rule. Keep the 6, the negative 6 rather, power rule x squared over 2. 1 is a constant, but if we have a constant, then if we find the integral, we're going to be increasing the degree by 1. So a constant becomes constant times x. So same thing with number 4. A constant of 1 becomes constant times x. And then finally, we don't want to forget the plus c. And then simplify further, we get 3x cubed minus 3x squared plus x plus c. Okay, finally, number 5. We have x plus 1 divided by square root of x. Okay. Right now, we don't know how to deal with individual a fraction as a function of each other. There is no chain rule, okay, for integrals. So we're going to try and adapt this just like we did with number 4 to see if we can rewrite it as individual terms. And this is always possible with a fraction as long as there's only one term in the denominator. So I'm going to first split up into individual fractions. Okay, so I can write it as x over square root of x plus 1 over square root of x. Okay. I'm going to rewrite the square root of x as x to the 1/2. So now we have x over square root of 1/2 plus x to the 1/2. 1 over x to the 1/2 plus dx, or times dx. Okay. Simplify further. So I can subtract exponents. 1 minus 1/2 is simply 1/2. And just like the power rule with derivatives, we need variables to be sitting up in the numerator. So I need to move this denominator, this variable sitting in the denominator up to the top. So if I move the variable up, I'm also going to adjust my exponent. So now I get x to the negative 1/2. Okay. We have two separate terms now. We can apply the power rule separately for each. So we add 1 to the exponent. So 1/2 plus 1, the same thing as 1/2 plus 2 over 2, which is 3/2. So our new exponent, we have to make sure we divide by that new exponent following our power rule. X to the negative 1/2, we also apply the power rule. So negative 1/2 plus 1 becomes negative 1/2 plus 2 over 2, which is 1/2. So we divide also by our new exponent. And then we can begin to simplify. Okay. If we move the 3/2 to the top, we have to flip the fraction, so we get 2/3. If we want to bring the 1/2 up to the top, we have to take the reciprocal, so 2 over 1. So we get 2/3 x to the 3/2 plus 2 x to the 1/2 plus c. Or we can rewrite it as 2 square root of x cubed over 3 plus 2 square root of x plus c. So either form is fine. You just have to know how to identify it in case it's a multiple choice question.